The James Webb Space Telescope just captured something no human has ever seen, an image from the edge of the observable universe. Ancient light born just after the Big Bang is now visible for the first time. This isn't science fiction. It's a direct glimpse into the universe's first billion years. Peering into nothingness, we see the legacy of the ultra-deep field dot in 2004. Astronomers pointed the Hubble Space Telescope at a blank patch of sky near the constellation Fornax, a region with no bright stars, no galaxies, nothing of note. Many thought the effort pointless. But over the course of several days, Hubble's 2.4-meter mirror captured something that changed astronomy forever. What returned was the ultra-deep field, a small dark corner of sky that, upon long exposure, revealed over 10,000 galaxies. Each one was a cosmic city of stars spanning spiral arms, elliptical halos, and blue star-forming regions. What looked like nothing was, in fact, everything, an archive of cosmic history stretching back more than 13 billion years. But there were limits. Hubble, though revolutionary, could only see so far. Its instruments captured visible and ultraviolet light, but much of the early universe's glow had redshifted into the infrared wavelengths Hubble struggled to detect. The further away a galaxy is, the faster it recedes due to the expansion of the universe, stretching its light into longer, redder wavelengths. This made many early galaxies effectively invisible, and cosmic dust abundant in early star-forming regions blocked Hubble's view in key wavelengths. The ultra-deep field showed us a snapshot of adolescence, but it left out the cradle, the earliest moments of galaxy birth, the foggy dawn before light could travel freely. The ultra-deep field was like looking through a keyhole into the past, a limited angle, a single pixel in the cosmic portrait. The obvious question followed: were these galaxies rare outliers or just the tip of an unseen ocean? That's where Hubble left us, peering into the dark, wondering what we were still missing. And then came Webb. Enter Webb, a telescope of a new class. The James Webb Space Telescope, JWST, wasn't designed to replace Hubble. It was built to surpass it in the one domain Hubble couldn't reach: the infrared. Its 6.5-meter primary mirror is nearly 3 times wider than Hubble's, and it carries a sun shield the size of a tennis court. Webb is humanity's most advanced eye into the deep cosmos. It's not just bigger, it's colder. Sitting at Lagrange point 2, Webb stays shielded from Earth's heat, allowing its instruments to cool to near absolute zero, necessary for detecting faint ancient infrared light. This is light emitted when the universe was still young, stretched by billions of years of expansion. Its science arsenal includes the near-infrared camera, NIRCam, and the mid-infrared instrument, MIRI, covering wavelengths from 0.6 to 28 microns, far beyond what Hubble could see. These tools allow Webb to cut through dust clouds and detect galaxies whose light began in the first few 100 million years after the Big Bang. But Webb's revolution isn't just about depth, it's about breadth. While Hubble focused on narrow fields, Webb can cover wider swaths of sky with greater detail, enabling statistical analysis of not just a few galaxies but hundreds of thousands. The approach shifted from finding individual outliers to mapping entire populations, revealing how galaxies form, evolve, and interact on a cosmic scale. Webb sees not just farther but clearer, making the invisible visible and turning the theoretical into the observable. And its first image would prove exactly what that meant. From engineering to discovery, the making of a revolutionary survey, the James Webb Space Telescope is a triumph of engineering born from the edge of impossibility. To work, it's 18 hexagonal. Mirror segments had to align with nanometer precision, less than the width of a virus. Its detectors, cooled to just above absolute zero, needed to detect the faintest signals of light ever captured from the early universe. Getting to space was just the beginning. After its flawless December 2021 launch, Webb underwent a 6-month commissioning phase, unfolding, aligning, and calibrating over 1 million miles from Earth. Only then could it begin its mission. But the vision for Webb went beyond depth. Led by astronomers like Caitlin Casey and John Cartoliti, the science teams didn't just want to peer into one dark corner of the sky. They wanted scale, to move. From snapshots to census, from isolated discoveries to full-blown galactic ecosystems. This shift demanded more than a powerful telescope. It required sophisticated data pipelines, custom software built to process terabytes of overlapping exposures. These tools had to detect and correct for instrumental artifacts, cosmic rays, and field distortions. Then images were stitched into seamless mosaics, each revealing deeper layers of the universe. Webb wasn't just imaging galaxies. It was counting them, mapping their shapes, distances, and redshifts. It was turning ancient light into measurable data ready for statistical analysis. This was critical because finding a few strange galaxies doesn't rewrite cosmology, but finding thousands with patterns, how they cluster and evolve, that changes everything. The old approach was narrow. Hubble showed us what was possible. Webb shows us what's typical, frequent, and sometimes completely unexpected. By combining vast surveys with cutting-edge sensitivity, Webb turned deep space from a mystery into a measurable domain. And when its first public image was released, it proved what those systems could do. The first Webb image offered a glimpse at the cosmic edge. On July 11, 2022, NASA unveiled the first deep-field image from Webb. The target, SMACS 0723, was a massive galaxy cluster acting as a gravitational lens, bending and magnifying the light of galaxies far behind it. The image was breathtaking. A region of sky no larger than a grain of sand held at arm's length was filled with thousands of galaxies. Some so redshifted they appeared stretched and smeared into glowing arcs. These were galaxies from the dawn of time, some seen as they were less than 1 billion years after the Big Bang. Others were distorted by the cluster's immense gravity, revealing details invisible in normal conditions. And this was just a tiny corner of the sky. In one exposure, Webb outperformed weeks of Hubble imaging, capturing light billions of years old with unprecedented sharpness. Those arcs weren't just pretty. They held information about the structure, mass, and evolution of galaxies formed during the universe's first epochs. Every red smear was a clue. Every distant dot a data point in a cosmic timeline. For astronomers, this image marked a turning point. The keyhole view was gone. Webb had kicked the door open, and behind it was not darkness, but the earliest light. This wasn't just a telescope working. It was the universe answering back. The Hubble ultra-deep field gave us a glimpse into deep time, but the area it covered was tiny, like looking through a soda straw into the sky. Webb, by contrast, doesn't just stare. It sweeps. Take the Cosmos Webb survey, one of Webb's flagship campaigns. It covers nearly 0.5 square degrees of sky, roughly the area of 3 full moons. Within that single survey, astronomers cataloged nearly 780,000 galaxies in one sweep. Each galaxy carries light from a different point in the universe's history. Some formed 300 million years after the Big Bang. Others were born billions of years later. Together, they represent a cosmic population census, allowing researchers to study how galaxies live, evolve, and die across cosmic time. Hubble's legacy was about finding the first galaxies. Webb's legacy is about understanding how many, how fast, and how different those galaxies were from expectations. In the Cosmos Webb field, astronomers found red, dusty, massive galaxies that Hubble simply couldn't detect. Some were already quenched, meaning they had stopped forming stars even when the universe was only a few billion years old. Theory had assumed that galaxies that early were still chaotic, hotbeds of star formation. Instead, Webb revealed a mixed picture. Calm spirals alongside violent mergers, young blue galaxies beside old red ones. In short, the early universe was already diverse, dynamic, and surprisingly mature.